The problem with the real numbers is that things are not always going to be in the right place. It's not like for the complex numbers where we have this really beautiful residue theorem and we can just, if we want to calculate the number of roots in a given closed region, we just instantly can do it using the residue theorem. When we try to count the number of real roots of a polynomial in a closed interval, we're going to have to do a lot of really complicated stuff. The complex numbers are what are called algebraically closed. That means that every polynomial of degree n in a complex variable z has n roots, where the roots are complex numbers. For the real numbers, it's not going to work like that. If you have an nth degree polynomial where the variables are real numbers, then it's going to have n roots, where the roots are counted with their multiplicities, but some of the roots are going to be real numbers and some of them are going to be complex numbers. So in order to capture all of the roots, you need to extend the field of real numbers by using the imaginary number I. And the most important part about the imaginary number I is that it generates the group of rotations around the origin by 90 degrees. Instead of thinking about each positive real number as a way to measure the distance between 2 points, it's better to think of each positive real number as a way of mapping the entire real line into itself. There's two ways that we could map the entire real line into itself. We can either translate every point, or we could scale the entire real line. When we translate, then we could have some real number a, and then just take everything on the real line and just push it over by a. And when we scale everything, then we're going to just take every point on the real line and multiply it by some real number a. The number 1, now it becomes a transformation where we map the entire real line into itself without doing anything. And if we use the function e to the t, where t is any real number, then we see that 1 is equal to e to the 0. And every way of shrinking or expanding the entire real line in order to map it to itself can be captured by starting from the identity element e to the 0, and then it can be continuously developed by just continuously varying t until we reach the scaling transformation that we want. But there's another way to map the entire real line into itself which is not continuous, and that's to switch our conception of left-handed and right-handed. So instead of having all of the negatives go off to the left and all the positives going off to the right, it's going to be switched. So now all the negatives go off to the right and the positives are going off to the left. And if you think about it, there's no way to start from a place where left hand and right hand have their normal meanings and then continuously map the entire real line into itself in such a way that now left hand and right hand got swapped. And so we really need to divide the group of all the real numbers into these two cases. When we multiply the real line by a negative real number, then left and right hand get switched. And we need to figure out a way to make that operation of switching left and right hand for the real line continuous. And the way we're going to do it is just take the real line and then rotate it by 90 degrees, and then rotate it in the same direction by 90 degrees again. And that's why we need the imaginary number I, in order to kind of put those two parts of the real line that we separated out back together again. In order to see that, we can write -1 as e to the I pi. So for any real number, if we're allowed to add I times some other real number, we're going to be able to continuously develop any sort of transformation from the identity where the left and right hand of the real line got switched. So maybe a good way to think about the real numbers is that the identity element is a point on a surface where we can take derivatives, and in the neighborhood of the region surrounding the identity element on this surface, there's a tangent space that has two vectors, and those two tangent vectors are 1 and I. And then the exponential function is a mapping, which allows us to start from the identity element and then move continuously from the identity element on a continuous path to any other transformation of the entire real line into itself. And that means that on this surface, which represents the group of all real numbers, when viewed as transformations which map the entire real line into itself, that the complex plane itself is the tangent space to the identity. And in that tangent space, for the group of real numbers, the operation is addition, and the identity element is 0. But when you use the exponential mapping, it takes you from the addition world into the world of multiplication, where the identity element is 1.